Guys, in this video I'm gonna explain about material deformation and fatigue. This video is gonna be based on the book Mechanical Behavior of Materials. Here you can see in this stress-strain chart a material behavior under some forces. In the y-axis is the stress, which is the force that we are applying to the material. In the x-axis is the strain, which is the deformation of the material. The stress is usually measured in megapascal, but can also be measured in Newton millimeters squared. In the strain axis, it's usually measured in percentage, but can be measured in millimeters or inches, depending on the type of the test. In this chart, we can see this generic curve. This almost straight line is the elastic region, which is the material can bend and return in its original shape. Here is the yield strength. It's the point that's the transition between the elastic region and the plastic region. In this plastic region, the material can bend and doesn't return in its original shape. Here, in this top point, is the final strength, which is the maximum force that the material can hold without starts knacking and then breaks. I have here a paper clip, which it's a normal paper clip. If we bend this paper clip like this, you can see that the clip is returned to its original shape. So this returning to its original shape is this elastic region here. If we bend more than that, it will not return in its original shape. So it's past the elastic region and entered a plastic region. So this curve here, the more up the curve is, the more rigid the material is. Like glass or iron, this ultimate strength here, the higher that is, the more mechanical resistance the material have. This curve is get in a machine that stretch the material until it breaks and measure all the points until you have this final curve. This is a generic curve depending on the material, like some plastics or nylon or aluminum, steel. The curve will change its shape. Here I have a piece of sponge that represents a test in this machine. So the machine holds the bottom part of the sample and the upper part of the sample. The machine starts stretching until it breaks. If you look closely, the material in the middle part, when you pull, the middle part necking. What's necking? The middle part starts to get thinner, like here. When it starts to get thinner, it's this part here, from here to here, until it breaks. So this is called necking. Here is a picture of two samples of materials. The material on the left is a softer material, a ductile material that starts to necking before breaking. The material on the right is a fragile material that doesn't have a neck, just breaks. Now I will show you some types of different curves here. This curve represents a glass or a piece of very fragile material like iron. So the material doesn't have the plastic region, and as soon as it's finished the elastic region, the material breaks. Here we have this curve that represents perhaps a piece of aluminum. So the aluminum have a small part of elastic region and already starts to deforming permanently. So this whole part here is the plastic region that doesn't return in its original shape. In this curve we have a very straight line represents perhaps some part of rubber or sponge like this one that doesn't have any plastic or almost any plastic region. So as you can see, we can bend the sponge and return. This sponge doesn't have the plastic region. The curve can be in different places based on the temperature. Let's say that this is a piece of steel and we freeze the steel. So the curve will be more in this direction. If we heat this piece of steel, the curve will be more in this direction. So you can alter the position of the curve based on the temperature. So this is a Waller curve. In the y-axis is the stress, the force that you are applying to the material. In the x-axis is the number of cycles that you are applying a force to this material. The test to make this curve can be by bending the material, flexion, by twisting, torsion, by compression, and by traction to obtain this curve. At the beginning, you design the material and you're applying force to flex the material like this. And at the beginning, the material holds the number of cycles. As the number of cycles increase, the material starts to make a little cracks inside, like this picture. Cracks very small, 10 times smaller than a human hair. And these cracks starts to growing and growing until the material breaks. Let's take this steel for example. It starts its life here, and as the number of cycles increases, the steel tends to lose its force through time. So here in this elbow, the steel stabilizes and go on to infinite life. So the steel, in this case, is half of the force that it started. If we take aluminum, for example, it starts here, makes an elbow, and doesn't flat the curve. Always will be taking less force to create these small cracks in the aluminum. So eventually the aluminum, in this case, will break. The steel, if you apply the force that is half of the first force, the steel is gonna survive. It also depends on how this material is gonna be used. Let's say that the surface finishing of this material is very smooth versus a very rough surface finishing. The smoother finish of the surface is better to not create these cracks. If you are using this material, this part, in a corrosive ambient, it also increases the chance to create these small cracks. The shape of the part is also important. Let's say that we have an axle here and then got a smaller section at the end. Here we concentrate tensions that leads to these small cracks. Temperature changes also leads to these small cracks as we increase the temperature or decrease the temperature. So that's it for this video. Take a look at that book for more information.